the next problem directly asks for the next larger value. Now the problem statement is again, kind of irritating because uh, they, they haven't been concise here. So we will first work on a slightly more elegant version of this problem, and then we will come back and look at what format they want the output to be in, and then make changes. But the concise problem is that you are given an array of integers, and this array has unique integers. Okay, so pretend that you're given an array with unique integers. What you want to find is, for each element in the array, you want to find the next larger value. Instead of the previous larger value, you want to find the next larger value. And let's say you store that next larger value in some way. Maybe you store a mapping for every element. What is the next larger value in the array? Let's say you want to just determine that and just give me the mappings in whatever way you want. Maybe you will finally store it in a hash map. Maybe you'll finally store it in an array like you did in the first problem. So let's first work on that. Now, what is the next larger value? The next larger value means when we look to the right instead of looking to the left as we were for finding the previous larger value. For the next larger value, we will look on the right side and identify the very first number we see that's bigger than our number. Right? So the first greater number to the right side, on the right side instead of the left side, is the next larger value. So we will assume that the array we are given is called nums2, and ignore nums1 for a few minutes. Let's solve this problem and then come back and then handle the needless complication that they've introduced here. So this is classified as an easy problem, probably because the brute force solution is what they are expecting, but we want to find, let's add this constraint up front. We want to find the next larger value for each element in the given array in linear time. So let's summarize that. Given an array of integers called nums2, compute and return the next larger value for every element in it. In linear time. So that is the concise description of the problem. So the only change, therefore, from the previous two problems is we want to find the larger value, first larger value we see on the right side instead of on the left side. So on the surface, that doesn't seem to be changing anything, right? I mean, if you were to just take the array and imagine, if it was in 3D space, just imagine walking behind it and looking at it from the back side. Then what is the next larger value from the front is going to appear to be the previous larger value from the back side. So one would expect that the code for this is going to be identical or almost identical to the code for the finding the previous larger value for each element. Could somebody guess what is the small change that you would need to make to find the next larger value? Okay, Soumya. Hold on, I don't see your hand here. Yeah, Soumya.
Yeah, hi. So we can we need to basically swipe the basically browse through from right to left,
Exactly.
and yeah, and we need to keep any number which is greater than our number. We need to keep it in the stack.
Right. Exactly. So the only change is we just go right to left instead of left to right, and that would solve the problem. So we will have our stack as usual. Right. Let's again. I'm trying to stick to the code that we had written. Well, let's go back to the first problem. Since again we're given an array here. Um, okay. So we initialize an empty stack, and then for each element in the array, while the stack is not empty and the element at the top of the stack is less than or equal to our current element, we pop the stack. And then once we exit the while loop, we would be at the next larger value, or you can say the previous larger value in this problem. But if we go right to left, that's like going left to right from the backside. If we when you're looking at the array from the backside, so nothing would change. It's just that the direction would be right to left, and the index you're starting from would be n minus 1 instead of 0. So you would continue to process the next larger value in whatever way you want. In this case, we want to store the mapping between the for each element we want to identify what's the next larger value, and we want to return that mapping. Let's say we want to return it in a hash table. So we will store add an entry to the hash table here, and then we continue to insert the current element into the monotonic stack, and finally we'll just return the mapping right at the end of this for loop. So that's all we are planning to do. Let's write the code for this. So we are going to have a for loop going from right to left instead of left to right. So uh, n here is the length of the array we are given. So I'm just going to write it as length of nums2 minus 1, right? That's the starting index, n minus 1, down to 0. So for each value in the right to left order, what we want to do is to find the next larger value. So the ith manager is focused on the number at index I is going to be computing the next larger value for nums of I, right? And storing it in a some kind of mapping. So we'll use the same template while the stack is not empty, and the top of the stack. So as we are going from right to left, we are storing the elements in decreasing order, right? Just like we did in finding the previous larger value. Um, so while the stack is not empty and the element at the top of the stack now in this problem, uh, we don't really care about the indices, right? Otherwise we would have a pair inserted into the stack, but in this particular problem, if you like, we can add the indices, but because all the values are unique, uh, for every element the next larger element will also there will be a unique mapping, right? There'll be a unique key, and whatever the value is will also be well, the value may be the same for two different elements. Maybe the next larger value uh, Uh, well, can it be the same? Well, it can't be the same, right? Because if one of the elements, yeah, the next larger value can't be the same. So both the domain and sort of the range of uh, the mapping are going to be unique values. So while st is not empty and the top of the stack is less than or equal to my current value, right? My current value is nums of I. I'm going to keep popping the stack. So when we exit this while loop, we would be staring at the next larger value for nums of I is at the top of the stack, if at all it exists, right? So if there is a possibility it might not exist because maybe all the values that we've seen so far have been less than or equal to our current value, in which case it wouldn't exist. But if it exists, obviously the stack will not be empty. So we want to process it. We want to process the next larger value by storing it in a mapping. Let's say we want to add it to a hash map, right? So if the stack is not empty, that's when we know the next larger value exists. So in that case, we will add it to a result to some kind of hash table. So let's assume the hash table is called result. It's initialized to be an empty dictionary. So we will just add a mapping to it. What is the key that we want to add for the mapping? Well, the key is nums of I, and the value is the next larger value for it. So the next larger value that we have determined is the value at the top of the stack. So that's just going to be whatever value we see at the top. There is also a chance though that the stack might be empty, right? That means the next larger value does not exist. So in that case, this particular problem specifies that you're supposed to return a -1. So again, since they have added that constraint, let's just stick with it. If it does not exist, then it needs to be a -1. Anyway, so we have processed the next larger value. Finally, we have to insert our current element. So let's not forget to do that. So we're going to push our current value into the stack. And so when the for loop terminates, let's see, just to avoid confusion, let me demarcate the block like this. So when the for loop terminates, the hash map called result stores the mapping. So we can return the result. And we would have solved this problem in linear time by the same argument that we've used for the earlier two problems. The auxiliary space used could be, would be order n again. The result mapping itself could be order n in size. So the monotonic stack here is different from the output itself, which is stored in a hash table. So both can be order n in size. So the space used is order n. Not just the auxiliary space, but the space used by the output as well. You might recall that, generally speaking, wherever there is a confusion, always remember that when we talk about space complexity, you can always clarify with the interviewer, so there is some space that the input uses, which is often not counted in space complexity. But if you want to be nitpicky, you would count the space used by the input, the space used by the output, auxiliary space that you use, intermediate space that is used for computing the output. That's auxiliary space. And finally, any implicit space that you use in the call stack. So in this case, the auxiliary space used is for the monotonic stack, that's order n. The output space is used by the hash table, that's order n. There is no recursion, so no call stack space. And let's assume the input space doesn't is not to be included. Okay, so any questions about this? I'll go back to the actual problem given here, but
quick question, like
yeah,
quick comment basically. So this requires like for each index, give me the next higher. It's not for each value, right? So maybe we should put like
for each index. Yeah.
So in the maybe for the key, we can use the index only.
Yeah. The thing is, the array has unique integers.
Oh, unique.
So,
okay. In that case,
yeah. Okay. Because let me add that also. All the integers are unique. So that means for every value that you see in the array, there's a unique next larger value.
Okay. Yeah. Thanks.
Yeah. Soumya?
Yeah, sorry, I forgot to.
Okay. Yeah, Abhinav?
Yeah, I was attempting this question iterating left to right, and my guess is that can also give a correct solution. We just peek the stack. If the value is greater than the current value, then we have a right greater. Am I thinking correct, or there's a gap there?
Yeah, in this case, because so you're saying you'll build a previous value and then you will like invert the mapping. Is that
so?
You'll go left to right, build a mapping for the.
Yeah, I'll go left to right. If stack is not empty and stack top is greater than the current value, that means I have a solution for the stack top that is right greater.
So hold on. When you say you're changing this also, you're making this greater than. Is that what you said? St dot top is. Sorry, I guess you can't see my cursor.
So actually, it should be less than. Yeah, I was thinking incorrectly. So if stack top is less than current value, when I'm iterating left to right, then current value is a right greater of whatever was on the stack. So I'll put that mapping into a hash map.
Okay, just try it out and see, because I'm like I'll need to spend a few minutes thinking about whether or not that works, but it's just try it and see if it works. I'm trying to stick to, minimal changes from what I've done so that the cognitive load is as low as possible here.
Yeah,
so,
that makes sense.
Yeah. So, yeah, just trying to be lazy. So now let's go back to the previous, the problem description here. You're actually given two arrays here, nums1 and nums2, and you are supposed to find the next larger value for each element in nums2. But then, you're supposed to look at the first array, nums1, whose elements are given to be a subset of the elements of nums2. Right? Nums1 is given to be a subset of nums2. So in other words, they don't finally want the mapping for all the elements in nums2. They want you to look at whatever values are in nums1 and generate like an output just for that subset of elements. Okay, so it's a complicated way to put it, but basically for every value that you see in nums1, go to nums2 and determine you're guaranteed that this value is going to be found in nums2. So go to nums2 and determine the next greater element of that value in nums2. Right. So we have already computed the next larger element for every value in nums2. So we just have to go through nums1 for every value that we see in nums1. We just look up the mapping, since we've already done the work of computing all the next, all the values from of the successors from nums2. Just for every value in nums1, consult that mapping to determine what's the next larger value in nums2 for it, and you just append it to an output, right? So they want the output specifically in an array called answer. So for every element in nums1, you would actually add to this or append to this array the next larger value of that element in the nums2 array, right? So very verbose and a bit confusing, but ultimately what you have to do is for every value in nums1, for every number in the nums1 array, right? Iterate through the nums1 array for every number. Look at the mapping. You're guaranteed that this number exists in the nums2 array, and you already have a mapping for the next larger value for that number in the nums2 array. So just look at that mapping. So I'm just going to look up that mapping, right? I pass this as a key to the hash map, and I'm going to get back the value, which is the next larger value of num in nums2. And I need to append it to an answer array. This answer array obviously starts out being empty, and by the end of this for loop, it would have been filled with all the next larger values. So we return the answer, the answer array. So how much time? So this part we know took time proportional to the length of nums2. Here we are looking at every element in nums1 and just looking up the mapping to fill in the answer array. So this part of the code takes time proportional to the length of nums1. So when combined together, the total code takes time proportional to the sum of the lengths of the two arrays, which is what they want. Space wise, we are using extra space. The answer array itself will have a size proportional to the length of nums1, equal to the length of nums1 actually. And the hash map has a size that is equal to or proportional to the length of nums2. And the monotonic stack also has a size that is proportional to in the worst case, that's going to be order of the length of nums2. So they say it's an easy problem, but it's not really easy, because typically it's the follow-up that makes the problem harder. So if you don't use a monotonic stack solution, you would just be using a brute force approach, which will take you quadratic time. So for each element in nums1, you might end up taking time that is proportional to the length of nums2, because you would search for that element in nums2 first, and then when you find it, you look at its right and see what's the next larger value. So that will take time proportional to the product of the lengths of the two arrays, that brute force approach. So the follow-up asks you to do it in linear time, and because how do you know we should use a monotonic stack? Um this is the claim. So in this problem, we needed the next larger value, right? So far we now know uh, that if we need the previous larger value for every element, if we need the next larger value for every element in the array, it makes sense to use a monotonic stack. Ashok?
Yeah, can we go back to the previous code we wrote? Yeah. So in this, when we start looping through the array from right to left, let's think about the first element on the rightmost element. So
Right.
are we not storing coming to the else part of the if statement?
Yes. So for the rightmost element, there won't exist a next larger value because there is no value. There is no next value itself, right? So there's no question of a next larger value, and there is no next value on the right side.
Okay. Thank you.
Next just means on the right side, previous means towards the left. Balaji?
So,
No.
sorry.
Yeah, sorry, there are two Balajis.
Yeah, so I was asked this problem in one of the interviews. So the one thing that is confusing is if it was not for that other array, it's like any other monotonic stack. It's when I read the problem, the nums1 array confused me because in order to say if the nums1 array elements are not in the same order as nums2 array, then it is misleading in that it may not be a monotonic stack. So that's what got me confusing. But if you were to pre-process nums2 and then do a lookup on nums1, I think it makes sense now. So.
Yeah.
But the one thing is brute force versus the approach that you suggested. It's a trade-off between time and space complexity, right?
Yes.
In brute
Yes.
force, it's not. There's no additional space.
Yeah. So monotonic stacks will always use extra space. Garrett? By the way, which company asked you that, Balaji?
Rivian.
Okay. It was the same exact problem. They just copied
Yeah,
what is it?
same exact problem. Yeah, they just added some car stuff in there, but yeah, it reduces to the same problem.
Okay.
So
Uh,
my confusion arises, and I just want to be sure. If we are looking for the previous largest number, so I just call this, I'm looking for my left largest number, then I scan from left to right. If I'm looking for my next or right largest number, then I scan from right to left. Is there any exception to the rule? Because I think the part of the challenge is that I'm also trying to figure out, like, do I scan from left to right or right to left?
Well, so since this is like a bottom-up approach where you are waiting for other people to have computed the answer before you compute the answer for your number, if you are looking for an answer that lies on the right side, then assume that the work is going to be handed, the information is going to come to you from the right side, so that just like in the first problem. So if you are searching for the next value, right, whether it's larger or smaller, we look at the smaller later. That means you want a value on the right side that is bigger than your number. So assume that you'll be scanning from the right side, so that uh, people on your right have already computed the next larger value for their respective numbers. And so they just hand you this data structure, a monotonic stack, using which you can quickly get your answer. Whereas if people on your left had computed the answer, right, it doesn't tell you what lies, like what part of that data structure, whatever they're passing you, what part pertains only to the numbers that are exclusively to your right, because your own value could be corrupting. It's present in that data structure, so it might be a bit corrupting. So that's one way you can think about it.
Okay. So it
Yeah, so
sounds
it's
like if I'm the lazy manager and I do not know what to do, then I look at both my left and right, and the subordinate that gives me the information that allows me to do all of one work will be the right direction to start from.
yes. So
Okay.
yeah, and yeah, here it's average O of 1. Obviously, an individual manager might end up doing more, but collectively, on average, they end up doing O of 1 work.
Okay. Thank you. This has been helpful. Thanks.
Balaji, I assume your question's answered. You could lower your hand. Yita Lee.
Hey, Omkar. I just have a quick question. Let's say I change the question a little bit, saying instead of return the next greater element, we return all the greater element. So I know if we change this question, then we cannot use a monotonic stack. But I just come up with a solution saying we probably can preprocess the nums tool and build like a binary search tree. And since the question asking return all the greater element, then we can just based on the nums one and find the node and just return all of the greater element from the binary search tree. Is this solution correct?
So I think it wouldn't be any better than brute force, because let's say you want to return all the elements on the right side that are bigger. In the worst case, they just could be every single element on the right side for every single number. So if the array, for example, is sorted already, then for every number, all the numbers on the right side would be, bigger than it. And so if you were to store that mapping for each number, that would be quadratic in size. And since the output is already quadratic in size, there is no way you can create a quadratic sized output in less than quadratic time, which means a brute force approach is the best you can do. I mean, there's no point in trying to improve the brute force given that the output size is already going to be quadratic in the worst case.